And then I would like to also give the word to Professor Antonio Cala Lesina from the University of Hannover. I hope I pronounced the last name correctly. And he will host the amazing tutorial with Jelena Vuckovic from the University of Stanford. And yeah, I'm giving the word to Antonio. Thank you very much.
Thank you, Anne-Catherine, and welcome to the second tutorial of today. I'm so excited to share this tutorial, and we have another amazing speaker tonight, tonight for Europe. So Professor Jelena Vuckovic, who's a professor at Stanford, where she leads the Nanoscale and Quantum Photonics Lab. She's also the director of QFAR, the Stanford-SLAC Quantum Initiative. Vuckovic has won numerous awards, including the IET AF Harvey Prize, James P. Gordon Memorial Speakership from the OSA, Humboldt Prize, the Distinguished Scholar Award from the Max Planck Institute for Quantum Optics, Hans Fischer Senior Fellowship, the Presidential Early Career Award for Scientists and Engineers, and the Young Investigator Awards from DARPA and the Office of Naval Research. She is a fellow of the American Physical Society, of the Optical Society of America, and of the Institute of Electronics and Electrical Engineers. It's such a pleasure to leave the floor to Professor Vuckovic for her tutorial.
Thank you very much, Antonio, for the great introduction, and thank you and the other organizers, Andrea and Katrin, Orad, I hope I'm not forgetting anyone, for inviting me to this wonderful conference. I know everything is online these days, but you were the original online meeting, so I'm really honored to present here finally. As Antonio already mentioned, I will be talking about my work on optimization in photonics. And of course, there are many other groups around the world working on this, but this is something very close to my heart because it's kind of maybe one of the longest running projects in my group. We've been working on this for a really long time, although at first we were not really sure how to do things properly. So you'll see here some of the evolution and most recent results that we have, which are really enabling scalable photonics. And I will just start with something that all of you know. Of course, the photonics has many applications. That's why we're working on photonics. These are some of the most exciting ones maybe today that many of us are working on. Quantum technologies, optical interconnects, sensors, augmented reality, LiDAR, optical neural networks. I mean, we had a wonderful tutorial just before this one. But all of these implementations and applications really require integrated photonics, right? You can make some proof of concept demonstrations using maybe free space optics, but if you were to build something useful, for example, for augmented reality system, it has to fit into the footprint of your regular glasses. So you really need to integrate a lot of photonic components into a small chip. So how do you do that? How do you actually go from something like this? And this is my lab, my quantum optics experiment and my graduate student to something that looks like this. And of course, we've been working on integrated photonics, all of us for a long time. And this is kind of how the state of the art integrated photonics looks like, kind of more mainstream integrated photonics. You have some waveguides, you have some ring resonators, and then some modulators, some grating couplers. But we all know that photonics is pretty bulky. We have at least tens of microns per component. When electronic circuit designers see our photonics components, that's like a shock, you know, how much real estate on a chip you need for photonics as opposed to electronics. Also, you know, maybe even more critically, it's very sensitive to fabrication errors, to temperature variations. So we have to integrate all of these post-fabrication kind of post-tuners like heaters in order to tune everything on resonance once you make an integrated circuit. it is designed by manual tuning of few parameters. We all take optoelectronics, photonics classes as students, and then we learn about the library of components. And then when we work as photonics engineers or like research groups, we just take some things from the library and then put them together and tweak them a little bit, like separate distance, diameters, thickness, you know, but that's pretty much what we do. So it's a brute force tuning of few parameters, and there is no reason to believe that any of that is optimal, right? Now, nobody has proved that it's optimal. In fact, a lot of photonics components have photonics devices are designs inherited from microwave engineering, where people could only design things by hand. And we just transfer them to photonics designs. And of course, number of functionalities is limited. So if you were to design something new, something for a completely new function that you need in your system, then you may not have that in the library, and it may be really difficult to do it. And I'll show you some new functionalities that we've been addressing in recent years. And finally, you know, for a lot of applications, photonic devices that we have today are not sufficiently efficient. For example, you throw away even commercial photonic integrated circuits, more than 50% of the laser power on the incoming grading coupler, which is quite surprising. You know, when I started looking into more practical systems, I thought that you know, grading couplers are nearly 100% efficient, but it turns out that actually even in commercial systems, they are not. I mean, they're 40 to 50% efficient often. And for some applications, that's not a problem. But you know, in some applications, of course, throwing away 50% of the power is a big problem. You know, in quantum photonics, quantum technologies, that's half of your qubits that you're throwing away. And of course, in many other applications, I mean, that means that you have more power consumption, and that's not good for any like portable photonics technologies like augmented reality glasses. You also don't want to have photonic circuits consume a lot of power per bit for communication applications. For example, optical interconnects, even some of the state-of-the-art optical interconnect systems consume picojoule per bit, which is what people can also achieve with electronics. So it kind of beats the purpose of using photonics in applications where electronics is doing equally well. We really have to do better than that. But you know, these are not fundamental obstacles for photonics. I mean, it's just all coming from the fact that we're doing things the same. We've been doing things the same way for many decades, and we actually didn't even know whether we were doing it in an optimal way, which is why in my group, we've been wondering for a really long time whether we could do things in a better way, whether we could design photonic devices in an optimal way to make them robust to fabrication errors, to temperature variations, so that you know, you have higher yield of working devices once you make your chip, so that you can eliminate post-tuning elements like heaters, which consume additional power. Can you increase efficiency? Can you introduce new functionalities? Can you eliminate this brute force tuning from the manual parameter tuning from the design process? Can you actually make photonics even something that's more accessible to people without photonics expertise, like electronic circuit designers who are starting to use photonics for a variety of applications? And you know, as I mentioned, we've been working on this for a really long time in my group, and been thinking about this problem even as a graduate student, but that back then we didn't really know how to do optimization. Although I published a paper which is called optimization, but yeah, later realized that that's not an optimization, it's a brute force tuning, right? But about 8 years ago, we were finally able to do optimization for arbitrary 3-dimensional devices by searching the full parameter space. And this is something that I'm really the most excited about, because everything that we've done so far has shown us that the parameter space is so rich that when you are searching through the whole parameter space of things that you can fabricate in 3 dimensions, you're coming up with so many solutions that are much better than the things that we've been doing. And I'll show you that in a moment, that it is telling you that we have been doing everything in such a suboptimal way for decades, and that there's so many more opportunities for photonics going forward that we are seeing because of the way we're doing things now. So I'll tell you about this in a moment. We call this inverse design in photonics because we are defining what we would like to have and then searching the full parameter space to find the solution. And if you are new to the field, we wrote a couple of years ago, we Alejandro Rodriguez review paper for Nature Photonics about inverse design in photonics and this growing field, and a lot of new directions that people are taking in doing this research. And it also covers history of inverse design. So please read this review paper. It's still mostly up to date. So let me just go through the first few examples to kind of explain you what we're doing. This is pretty simple, right? But let's say you want to make a waveguide band, right? And it's kind of a rudimentary component for a photonic integrated circuit. And if you're making complex circuit, then you have to make some bands on the circuit. You can't connect everything with straight lines. And if you just don't know anything about photonics, you may just try to make 90 degrees angle on your waveguide. And as we probably all of us know here on the call, that's not going to be efficient. You're going to lose most of your power at that corner, right? And then if you took a photonics class, you probably, or even if you didn't take a photonics class, if you just follow your intuition, you would say, well, I should curve that corner. That's got to be better, right? And of course, you know, if you just curve that corner, it's going to be better, but you know, it's still every corner you lose 17% of your power. And you know, if you're making a more complicated circuit, that's not going to work very well, right? But it's better, right? You're going in the right direction. And then if you took photonics class, you know that radius of curvature is very important. So then you're going to make a really big band, right, of your waveguide. And that's going to be nearly 100% efficient, right? But of course, it's a very large radius of curvature, and this is going to take up so much of your chip space, real estate on your chip, that you know it's hard to believe that that's the best that we can do, right? But this is what we were taught to do in school, right, in photonics classes. And instead of doing that, you know, you can explore a variety of other, you know, corners. People have done beautiful work by brute forcing waveguide bands in photonic crystals, for example. I mean, that was one of the motivations of the original photonic crystal work, but that's pretty much all brute forced. You know, what if you have your regular waveguide at the input, rectangular cross section, and also at the output, and you would like to maximize transmission in a small footprint, maybe 2 by 2 microns, right? How can I do that? Do I know how to do that? You know, it turns out that if you try to search the optimal design for this 2 by 2 microns footprint, and if you just pixelate them into something like 40 nanometer pixels, right, which is kind of pretty decent for photonic device, and then you search all the combinations of these pixels, like silicon and air or silicon and oxide, and you say, well, you know, one combination of these pixels maybe works as a waveguide band. I mean, yeah, in principle, maybe you can design something that works as a waveguide band by using this approach. But the problem is that you have, even for such a tiny component, 2 to the power of 2,500 possible designs. And you have to simulate all of these in order to find the solution that works, right? And that also tells you that by using this approach, brute force approach, even for very simple devices, unless you're extremely lucky, you're not going to find the solution that works. But it's also telling you that the parameter space is enormous, right? And if you were to find the solution, you still need to search through that enormous parameter space. But how do you search through the parameter space? Well, you need to do something smarter than brute force search. And that's where we actually use gradient-based optimization, which is really like classical optimization, variety of classical optimization techniques that people use for many other problems in business and predictions of various processes, and optimization for electronic circuit, for packaging, variety of things, right? We are just applying the same equations to the problem in photonics optimization. And in fact, one of our collaborators from Stanford, who is a classical optimization expert, Stephen Boyd, I mean, has a optimization software, CVX, which is also used in SpaceX program for guiding rockets, right? So anyway, that's used broadly in many other applications, but we're just using it for photonics. So how do you do that? Well, if you were to design your waveguide band, for example, you still need to design this 2 by 2 micron structure, and you need to travel through that enormous parameter space, but you just don't want to travel to that randomly. You don't want to be blindfolded. You want to travel guided by the gradient of some figure of merit that you define. And your figure of merit or your cost function depends on what you were designing. You know, in this case, you incorporate efficiency, transmission efficiency. I mean, that's what you would like to have: maximum power, minimum reflection. You want to have, you can incorporate also a variety of constraints, as I'll show in a moment: minimum feature sizes, robustness to temperature variations, refractive index changes, fabrication errors. We do constrained optimization. But the bottom line is that you are, start from some random initial structure, you calculate gradients, they tell you which pixels in that structure you should preferentially change to make the maximum effect. And then you update the structure, resimulate, keep going, right? And we do that in about 400 or 500 cycles. And in each cycle, clearly you have to do electromagnetic simulations. So that's telling you that in order to optimize, I mean, this is better than brute force, but you still need to do about 1,000 electromagnetic simulations. And in order to calculate gradients, we use a clever trick that is called adjoint optimization, which allows you to calculate all the gradients just from 2 electromagnetic simulations, forward and backward simulation. And that has a lot of overlap with basically machine learning and backpropagation and neural network training. These are the same ideas, and people have written papers about that. But in our case, we just do 2 electromagnetic simulations. And from these 2 simulations, which we call forward and adjoint simulation, we can calculate all the gradients, and that tells us how to update the structure, and then we keep going. So again, for simulating and designing the device like this, you have to go through a few hundred cycles. Here is telling you how you are kind of changing the structure until you get to the one that satisfies your figure of merit and your design criteria. And the final solution is shown here. And then the final solution with electromagnetic field propagation is actually shown on the right. And for problems like this, generally, there are a lot more than one solution, which is telling you that parameter space is pretty large. I will be showing you these movies and pictures that look 2-dimensional, but keep in mind that everything that we do is actually 3-dimensional. So we constrain pattern to 2-dimensional pattern, but that is actually through a guiding layer of the structure. And sometimes we design the structures that have multiple aligned layers, but everything is done in 3-dimension to capture all of the losses of the system and all of the properties. You have to do that. So this is just a crosscut. For most of the problems, we just do single pattern because that's easiest to fabricate. But recently we've been doing grating couplers with 2 aligned layers, and we are even fabricating them in a foundry. So here is another example, mode converter. You convert first order mode from the input waveguide to the second order mode in the output waveguide, something that we traditionally do by adiabatic mode conversion, by kind of slowly expanding the waveguide adiabatically, and that takes hundreds of micrometers of the chip footprint. Here, we want to do it in a 2x1 micron device, and we're actually doing it again by optimization. This is the first stage of optimization. On the left, you see how your structure evolves. On right, you see how your field evolves as structure is changing. This is just the first step where you vary refractive index continuously, but that's not really yet the final solution because nobody can make this. And this is the second stage of fabrication constrained optimization, where you go to a binary pattern and you incorporate fabrication constraints like minimum feature sizes and whatever constrains your figure of merit. And here is the final field pattern on the right, which is actually a mode conversion. Full optimization, in this case, we have 400 iterations. Each iteration with 2 electromagnetic simulations takes about 1 hour on gaming GPUs for this. And that's kind of very reasonable amount of time. We had to work on hard to develop fast electromagnetic solvers and also fast optimization techniques in order to enable that, because we really want to have very fast turnaround time for this. And we think that we should be able to speed this up on gaming GPUs even by a factor of 10. And again, this is not the supercomputer, no scientific grade GPUs, just gaming GPUs that cost about $2,000 and or even less from NVIDIA. So another important note here is that efficiency is part of the figure of merit. So if you find a solution that is 3% efficient but compact, that we don't consider that as a solution. So we don't stop until we reach the target efficiency, which in the previous case was 90% for mode converter. And using this process, we designed a lot of different devices. This is a wavelength splitter where you would like to split 1.3 from 1.5 microns. And here is how the structure changes as you're optimizing it. You will see this is 2.8 by 2.8 micron structure. That's one of the solutions that you see on the screen now changing in time as you're optimizing. Another solution is behind me. We fabricated a different solution. But it turns out that interestingly, in a 2.8 by 2.8 micron footprint for this particular function, we found 6 solutions that were equally efficient. And considering that this is at least a factor of 10 smaller than traditional WDM device, that's telling you that, you know, the parameter space is so rich that there are so many other solutions that you can find that we should be really exploring them, right? So that's the other solution with the same efficiency that we fabricated in silicon on insulator. Again, we're optimizing two-dimensional pattern, but by keeping in mind that this is a slab and all the simulations are run in 3 dimensions. So this one was fabricated by my students at Stanford with input and output waveguides, and then with superimposed field patterns. And when you, this was designed so that it has broadband behavior. First 100 nanometers, around 1.3 microns were transmitted to one output port, then the other into the bottom output port. So this is theoretically predicted or simulated behavior for the field. So it's performing WDM function. And then, you know, when you fabricate and measure them, that's exactly what happens. And I should also mention here that when we measure them, we measured a lot of devices on the chip and they all perform the same. Although our fabrication is far from being perfect, right? So we are really not fabricating devices that are perfectly identical to each other. And as we all know, you know, when you do photonics, when you fabricate it even in a foundry, not all devices perform the same. They're not really lined up and you have to tune them on resonances. But here, even without any post-tuning, when we just measured and plotted transmission plots on top of each other, they perform the same, which was very exciting for us when we first saw it 6 years ago, because yield is much higher. You have to spend less time in a clean room. It's very motivating for graduate students. I mean, for all of us, right? And we're not ruining materials because we go and fabricate something that is it should work unless there is a catastrophic failure of the fabrication equipment. And we extended that subsequently into 3-channel WDM devices like the ones at the bottom. So this one is splitting 3 different wavelengths in the telecom band. Again, measured, this was fabricated also at Stanford. We measured them, they all line up on top of each other. The lines are thick because they line up. And since we've been developing this over many years, we developed software suite, which we call SPINS. Stanford Photonics Inverse Design Software. It can be licensed out of Stanford Office of Technology Licensing, and many major companies and research groups, academic research groups and government labs are using it. We also have a free open source version, SPINS-B. That's the basic version. It's free, open source, can be downloaded on GitHub. It contains also electromagnetic solver, and you can actually download it and use it. So we're quite exciting. And recently we also released, you can actually go to the GitHub page, Jaxville, which is electromagnetic solver done on Jax, this programming platform for AI. So you can actually download all of that and use it for free. Okay, so those are the early days of the development where we demonstrated some of the first WDM devices. Since then, we've shown that we can do a variety of devices for optical communications, and then new functionalities. I mean, I mentioned new functionalities. It's not just by making known devices more compact, more robust, and so on, or more efficient. We also wanted to develop new functionalities such as laser-driven particle accelerator on a chip. I mean, I'll mention that in a moment, or non-reciprocal pulse router. I mean, we had no idea how to do this by hand, and that's why we used inverse design. And finally, which is very important for scalable systems, we've shown over the past 5 years or so that all of this is fully compatible with Foundry-based fabrication. And the approach is materials agnostic, although the structures on the top are all silicon, non-insulator based. In my group, we've also worked with inverse design structures in diamond and silicon carbide, but you can apply this to lithium niobate or any other material of choice that you're interested in. So first, foundry-based fabrication. Foundry-based fabrication is no different than university, e-beam fabrication. I mean, of course, when people first saw these patterns, they looked very non-intuitive and very strange, and they were concerned whether this could be fabricated in a foundry. But it turns out that that's not a problem at all. For foundry fabrication, of course, you have to run the design again. You have to start from the design rules from a particular foundry, and their feature sizes may not be the same as the ones that you can fabricate by your electron beam lithography. And in fact, that's usually the case. They're a little bit larger, but you redesign your devices with their fabrication constraints, and then you send them GDS files that have layout on the design devices. They run their design rule check again. They tell you if you need to change anything, but other than that, they can actually fabricate it on the chips using traditional process. So first we worked with AIM Photonics. We worked with Global Foundries and AIM Photonics, but first devices demonstrations were with AIM Photonics. We collaborated with John Bowers. For the first round, we just sent exactly the same designs and layouts that we already fabricated and measured at Stanford, like this 3-channel wavelength splitter. Here is the device we made at Stanford on the left. Here is a device made by AIM Photonics, same design in the middle, theoretically predicted behavior, and then measured behavior on the Foundry fabricated devices is on the right. Again, measured over many devices on the chip. They all perform the same. There is a slight degradation in performance relative to our devices from Stanford, and that's because at the time when we sent this chip, we didn't really know that AIM Photonics had minimum feature sizes of about 100 nanometers. We sent minimum feature sizes of 80 nanometers, which was our design, but with small correction, this could be actually improved. Nevertheless, it's not a big degradation. It's still working pretty well. This is another device from, we demonstrated in AIM Photonics, spatial mode splitter, converter. Here in a footprint of about 2 by 2 microns, you are splitting first order mode into the top left waveguide, and second order mode is converted to first order mode and sent to the bottom left waveguide. And this is something that you may use to capture more input polarizations from a fiber if you were using optical interconnect system. So here are the designs. We sent the layout with 2 cascaded devices. And of course, because of this behavior, you're predicting particular matrix for or mapping between 2 input and 2 output ports. Theoretically predicted behavior was insertion loss of 1.5 dB per device, right? 1 dB per device was theoretically predicted, or 2 dB total for cascade of 2 devices with excellent contrast between different ports. And then when we measured, we saw 1.5 dB per device. So this is measurement over many devices on a chip, 3 dB total for cascade of 2 devices. And again, the small discrepancy comes from these minimum feature sizes that were in the Foundry slightly larger than what we had thought. Since then, we've worked with a variety of other foundries, including Global Foundries and IME. These are some of the recent results with IME Foundry. We collaborated with Firouzah Flatuni, John Bowers. We're also collaborating with Alan Wilner from USC on high-speed measurements. This is optical interconnect system. We were working on DARPA-funded project for on-chip optical interconnects, and here we wanted to use mode division, multiplexing and demultiplexing to connect different parts of the electronic circuit. And doing by hand, mode division, multiplexers, demultiplexers is pretty hard. There are some solutions, but they're not very efficient. They're very large. As opposed to that, by inverse design, you can easily design these 4 by 4 micron elements that are doing this mode routing and conversion. And in fact, this mode conversion and mode splitting functions seem to be kind of ideally suited for inverse design. There is no mode conversion problem or mode routing problem that we couldn't really solve so far efficiently. So we're quite excited about it. I mean, the inverse design elements are in the box 2, and there is another one on the right in this red circle, and measurement is shown on the right. We see excellent suppression of channel crosstalk. We have here done kind of low speed measurement, but we are collaborating now with, again, UC Santa Barbara and USC on high speed measurement, and this should operate at 20 to 30 gigahertz. So it's fully compatible with Foundry, and you can actually do electronics and inverse design on the same chip. So now, going to new functionalities, which is something I mentioned before, apart from this Foundry-based fabrication, there were a few problems, and I'm sure all of us have problems when you have to come up with new functionalities for photonics, and you don't have off-the-shelf component that you can use for everything that you would like to do. So one of the problems that we were interested in was the problem of non-reciprocal routing and transmission. And we collaborated with Andrea Liu from City University of New York, who had this beautiful proposal and demonstration in the microwave regime for this non-reciprocal routing. So basically the idea is very simple. You cascade two resonators, one with Lorentzian transmission spectrum, one with Fano transmission spectrum, and you control phase delay between them. And Fano resonator has to be nonlinear, right? So you have some Kerr nonlinearity, for example. So if you design your system so that coupling in the forward and backward direction to your nonlinear resonator is different, then you would have a different wavelength shift of that transmission, Fano transmission. And at the frequency of your laser, you will have different transmission in the forward and backward direction. So it's kind of quite simple idea, and they demonstrated it in microwave circuits. But to do this well in optics, you clearly need some components that are not trivial to design by hand. You need right coupling efficiencies, you need particular transmission characteristics for the resonators and so on. So we decided to use the inverse design, and maybe if you spend a long time, you can do this by hand. Well, this is still a relatively simple problem, but by inverse design, you can really design it in a couple of hours. So we know that the underlying structure is two resonators coupled to a waveguide, right? But we want to control the transmission profile and couplings. So we just inverse design the coupling elements between resonator and the waveguide. And here you can see how that works. So just this region of the coupler here. Resonator itself didn't change because resonator is good enough already. But you want to do that in such a way that you're not degrading the Q factor of a resonator. And here you see movies how these coupling regions are changing, modifying as a function of optimization, while satisfying, again, feature sizes, minimum feature sizes, fabrication constraints. And figure of merit here is particular transmission efficiency and particular profile of transmission. The one on the left is here Fano resonance, and the one on the right is Lorentzian resonance. And when you finish the process, you have this layout that you need to fabricate, and fabricated pictures are also shown, and measured transmissions are also shown, and they satisfy our designed behavior. And then when you measure performance of this, you are expecting that you can transmit pulses in the forward direction. You're not transmitting them in the backward direction if you are in the right dynamic power range for the operation of the circuit. And indeed, that's what happens at the bottom. If you are outside of the dynamic power range, you are transmitted both forward and backward pulses. If you are in the right range, you're just transmitting forward pulses and blocking backward pulses. And we demonstrated that this works at 10 gigahertz rate. That's where we had the equipment for. In principle, can work at the 30 gigahertz rate. And I should just mention that this works in basically pulse regime or quasi-CW regime. There is a limit on pulse duration relative to the delay between the pulses. It doesn't really work as an isolator in a CW regime, but there are a lot of applications where you don't really need a perfect isolator. And one of those applications is optical ranging measurement, where you are measuring sending pulses in the forward direction and collected back reflection. And then you want to route those reflected pulses to your detector and measure delay. And based on that, do ranging measurement in a LiDAR. Of course, you can do this, implement this using a variety of switches, electro-optic modulators. I mean, you need basically circulator function and switching function here to route it to a detector. But here with our circuit, we can do the same with much smaller insertion loss than other solutions that people have, 0.17 dB insertion loss, very fast switching time comparable to the best like lithium niobate electro-optic modulators. And we basically have a fully passive circuit. So we don't really have other types of loss in our system as some of the isolator solutions are having. And footprint is extremely small. I mean, this is just a resonator. And here is the ranging measurement. I mean, it's kind of pretty simple. It's the same as what I showed you before, but we're doing ranging measurements up to 60-meter distance using this. So very simple solution here. You don't really need expensive electro-optic modulators, circulators for this. You can just make 2 extra resonators on the silicon circuit and do a ranging measurement. So that's one functionality. The other and completely new functionality that we looked into was on-chip integrated laser-driven particle accelerator. And here, this is, I mean, the old idea. We all know how accelerators work. You use some microwave radio frequency waves to accelerate particles. And each stage of acceleration accelerates these charged particles a little bit. So you accelerate them in the first stage and then go to the second stage and so on. And then, to go to mega electron volt or, giga electron volt or larger energies, you need miles of accelerator, right? So that's a simple idea. And then the idea that our A-chip team led by Bob Bayer and Peter Hommelhoff had was to go to optical frequencies and use infrared lasers instead of microwaves and radio frequency waves for acceleration. And simply by looking at the wavelength ratio between microwaves and optical waves, you can shrink this accelerator by a factor of 10,000, right? Because all the accelerator sizes of different stages in accelerator are proportional to the wavelength of electromagnetic waves used there. And for radio frequency waves or microwaves, that's 10,000 times larger than what we can do with infrared light. And that tells you that something like Stanford linear accelerator, which is 3 miles long, could be shrunk to a few inches of a wafer if everything works right? So you can actually have your portable accelerator on a chip, and which would be great for a variety of medical applications. But then, of course, the problem is you can't just shrink things, because you can't take microwave components and shrink them by a factor of 10,000. They're not going to work. You have to redesign stages of accelerator. And of course, we have no idea how to do that. There are no off-the-shelf accelerator components for laser-driven particle accelerators, which is why we used inverse design. We have to design this element here. This is a single stage of accelerator in such a way that for electrons that go through this vacuum region cut in a piece of semiconductor, electromagnetic fields, laser fields that are coupled to the structure would have the field profile that always accelerates electrons. So you don't want your field to accelerate and then decelerate electrons. It should always provide the kick in the right direction for the incoming electrons. And then the next stage has to be adapted to whatever speed you have. And on top of that, you'd have to design it in such a way that you can make it, right? I mean, there were some proposals for 3-dimensional photonic crystal-based acceleration, but that's, of course, really hard to make. So we wanted to do it in such a way that we can make it, and we decided to use silicon. And then you also need grating couplers that can couple your femtosecond pulses, very large bandwidth, very high power lasers without melting these couplers. So there are a lot of kind of non-traditional problems that you have to address here. But we managed to design it, and this 30 micrometer long stage basically provides the same acceleration gradient as some of the state-of-the-art accelerators, 30 mega electron volts per meter. And of course, this is just 30 microns, so there is not as much acceleration, but when you go to a few inches, you can go to mega electron volts. So we fabricated here everything, and here is the measurement. You look at the transmission of your electron beam without the laser turned on, the beam just goes through this structure. It's not accelerated. I mean, it's the same electron beam, same energy that you had at the tip. And here we do the experiment in converted electron beam microscope. So the incoming electrons have 83 kilo electron volt energy. But then when you turn the beam on, laser beam on, then you accelerate them, and you accelerate them by about 1.5 kilo electron volts within 30 microns chip distance. And when you divide that by 30 microns, that's 30 mega electron volts per meter. So if you cascade hundreds or thousands of these elements, these electrons, incoming electrons that are at 80 kilo electron volts, would be accelerated to mega electron volts. And that's already interesting for radiation therapy, for medicine, or even some imaging applications. And that's what we're working on now. So we only demonstrated single stage, but right now we're working with a Foundry on cascading multiple stages. And finally, I'd like to use kind of the last part of the talk, just showing you how you can use inverse design in other materials, primarily diamond and silicon carbide that my group has worked on, but it could be done in any other materials, basically, of your choice. We've done some work in collaboration with others on lithium niobate, tantala, and so on. But our work in my group has been only, in addition to silicon, on nitride and diamond and silicon carbide. And the reason why we're interested in diamond and silicon carbide is primarily in the context of quantum technologies. Basically, the idea is to build semiconductor quantum simulators and computers. And you're all familiar with beautiful work on superconducting quantum systems, including from leading companies like IBM and Google, or beautiful work on atomic quantum simulators. This is from the group of my colleague Emmanuel Bloch at Max Planck in Munich. And these systems have been scaled to several dozens of qubits or hundreds of qubits for quantum simulators. But of course, these are very complex systems. It's very difficult to scale them beyond where they are now. So we're hoping that we could transfer this to chip scale technologies like the ones that are shown on the right, where we use naturally trapped atoms, impurities in semiconductors as equivalents to Josephson junction qubits, or these atoms, neutral atoms trapped in vacuum. And of course, it's not just a chip, there is infrastructure around it, you have your cryostat, laser, and so on, but it's much simpler than for any of the other platforms that are currently leading. And again, the choice for us of the atom are impurities in diamond, like tin or silicon vacancy in diamond, where you remove two atoms and have impurity in between, or silicon vacancy in silicon carbide. But the topic of this talk is really photonics. So I'd like to use the opportunity to show you, a little bit of the inverse design photonics in diamond and in silicon carbide. So in diamond, they're, of course, working on quantum photonics or quantum systems. There are so many, it's even more pressing and more critical to have very high efficiency and to have, sort of very large robustness to any errors in fabrication, because every photon really here is matters much more than in classical devices. So that's why we had to design variety of elements. This is for the diamond photonics, inverse design diamond photonics. And this is three-dimensional bulk carving in diamond that we're doing at Stanford. And these elements here that are inverse design are some beam splitters and couplers and so on. And this dramatically improves the performance. Even if you redesign a coupler, you can have much higher collection efficiency. For this simple circuit with two couplers, we reduce our experimental time by a factor of 500, because efficiency of input and output coupling is increased by a factor of 25, 30. And that your signal to noise ratio is much better. You're not chasing your signal somewhere in the noise level, but you have much better signal to noise ratio. And you can think of scaling these systems much easier, because a lot of limits to scaling in quantum networks, for example, were limited by efficiencies of the system. We've also shown that you can do all of that with color centers inside without degrading properties of these color centers. Color centers are our qubits, our naturally trapped atoms, and you can do inverse design photonics together with your qubits, and it all works really well. And then also in silicon carbide, we're doing the same thing. And since many of you are interested in nonlinear optics or classical photonics, I'd also like to spend a moment to say that apart from quantum optics, silicon carbide is a very exciting material for photonics and nonlinear optics, because it has strong second order optical nonlinearity and third order nonlinearity. And it's also piezoelectric, has large band gap, excellent thermal conductivity. It's much cheaper than diamond, available on wafer scale from companies like Cree. Not commercially yet available as thin film, which is why we had to develop it, particularly for quantum optics applications. But as far as I know, some companies are coming out now with thin film silicon carbide and insulator. And that will, I'm sure, going forward, enable the same type of revolution in photonics that we've seen with thin film lithium niobate or silicon on insulator. And in particular, as opposed to silicon on insulator or thin film lithium niobate, silicon carbide is the only material that already has excellent qubits and offers all the combination of properties shown on top. Silicon doesn't have second order optical nonlinearity naturally. Lithium niobate does have, but doesn't have quantum emitters. So you can't really get all of this in one material other than silicon carbide. So I said we had to develop thin film silicon carbide. Again, I'm not going to go into details of that. We just bond silicon carbide, bulk silicon carbide onto oxidized silicon, and then we thin it, grind it, do fine tuning and thinning, and we can end up with few by few millimeter thin film silicon carbide wafers that are pristine. Quantum emitters are great inside as well. And this is, by some small modifications of the process, also scalable to do wafer scales. But for us, few by few millimeters is perfect. And at the moment, we can do inverse design in this. This is the inverse design structure, like coupler, for example, at the bottom left. We have Q factors in telecom range of greater than 5 million and loss of 0.08 dB per centimeter, which is comparable to actually like even Foundry-based nitride. So there is a lot of excitement here. Speaking of optimization, we kind of routinely use these optimized couplers. You see them here at the corner of the image. This is our first second harmonic generation experiment where we've demonstrated pretty good efficiency, but should be based on what we're doing right now, larger than that by a lot, 36% percent per watt, 36,000% per watt. We demonstrated OPO. I'll just quickly go through this. Again, there are inverse design couplers here as well with 8 milliwatt threshold. We demonstrated solitone comb recently, Chi3 solitone comb with, again, 2 milliwatts threshold. We also in the visible range have Q factors, visible wavelength range have Q factors of several 100,000. So that's all great. Quantum emitters are also there. They're not degraded. You can also do quantum photonics, but even if you're interested in nonlinear optics, there are a lot of exciting things to do even without quantum emitters. So now just to finish this, where are we going from here? I mean, I hopefully you are excited by the prospects of using optimization in photonics, but of course not all the problems have been solved, right? So everything I've shown you so far was more or less in this range of sizes up to kind of 10 microns or so in each direction in 3 dimensions. That's what we have been designing, and simply the reason why we've been focusing on that range is computational bottleneck. I'm sure most of you are doing electromagnetic simulations. When you go to larger devices, you need days to simulate them, right? Particularly if you were to simulate the whole meta surface, which is millimeters in size. So if you need days or weeks for one simulation, running 1,000 simulations in series is not really a really reasonable or practical way to optimize something, which means that you need to solve this computational bottleneck in order to enable efficient optimization of larger devices. And that's what we've been working on for a few years now. We've been combining some machine learning techniques with electromagnetic simulators to speed up just electromagnetic solution, find the right basis to solve electromagnetics of the problem. That can speed it up for the same range of devices we are using now, but then you again run into problems if you can't go into meta surfaces or so on. And then for meta surfaces, we're developing new solvers, transition matrix method solvers, which are really kind of suited for that particular problem. And they seem to be much, much faster than finite difference time domain solvers that are the only thing that kind of in principle works for meta surfaces, but blows up in time as you increase the simulation size. And the idea here is to kind of optimize the whole meta surface at once so that you also take into account any neighbor interactions that you would like to have, instead of doing it block or element by element or cell by cell as what people are doing now. We're also developing fast finite difference time domain solvers for based on GPU hardware, and hopefully combination of all of these variety of solvers and fast optimization tools will solve the computational bottleneck. And finally, we're also looking into applying these optimization techniques directly to quantum systems. When you look at all of the inverse design that we're doing, it's just an electromagnetic simulator, fast electromagnetic simulator, which is coupled with fast optimizer. And that's what's going through the whole parameter space and optimizing your photonics design. Now for quantum hardware design, we're developing open quantum system simulator, which is coupled with the optimizer. And the idea here is that you design something that has a particular Hamiltonian in the output. And again, this is, of course, not a quantum optics talk, but it's very similar to what we are doing in inverse design. There is no really strict barrier between developing quantum technologies and photonics. Photons are quantum particles or light. There are a lot of, pretty much all of the quantum technologies rely on some photonics or electromagnetics structures, at least for interconnections. So having something like this is quite important. And this would design some pulse sequences or some geometry of the structure in such a way that it works well. And using this, we already have some preliminary results which show us that for transduction, at least, transducing microwave to optical signals, we can do it with 20 times larger efficiency just by designing the right driving of our inhomogeneous ensembles that is used for this transaction purpose. So anyway, I mean, this is more like a future. I think that photonics design, inverse design can go beyond what I presented today, particularly on the quantum hardware design. And also with solving computational bottlenecks, we'll be able to design the whole circuit, millimeter circuit or metasurface going forward in the future. If you're interested in playing with software, again, there is an open source version on GitHub, basic version, SpinsB. You just go to my group's website and you'll find the link. There is also the version that could be licensed that, again, many companies and research groups are using. You can also license it out from Stanford. You can read also our reviews of that, like this article from last year where we explain what we're doing in spins. And really, while today's photonic integrated circuits kind of look like this, this is an example from the group of Derek England at MIT, maybe they'll be kind of quite different going forward and have many more these inverse designed elements, but not just prettier, in my opinion. They would actually be more energy efficient and robust and simpler and compact and practical. And with that, let me just thank you all for your attention again and thank my research group and our funding.
Thank you again, Professor Vuckovic. Amazing work. Your work has been so inspiring for the whole photonics community since basically one of your first papers on the design that you also show in your background. I have plenty of questions for you, so I'm going to read some of them. So Fulvio Flamini is asking, thank you very much for your talk. This is all really interesting. Have you ever studied whether you can transfer a solution learned for a specific task to a different but related task so that it's easier for the algorithm to solve the latter?
Yeah, that's an excellent question. I mean, in the context of speeding up optimization, we've been thinking of whether we can learn something from the solutions and can we initialize the process in a smarter way so that it converges the right solution better. For some problems, it's probably possible. Like if you're looking into something like mode conversion problems or wavelength splitting problems, but some problems are completely different. Geometry is completely different, parameter space is completely different, that it is hard for me to see that you can learn a lot from one problem and use it in a different problem. But we're looking into kind of generalizing, kind of finding some sort of mathematical explanation for maybe, hopefully general mathematical explanation for why certain solutions look certain way, with hope that that could help us initialize the problems better. We don't have the solution for that now, but we're doing research and we're also looking into problems on bounds, meaning, can you estimate in advance how large footprint has to be for a particular function and particular efficiency, how close you can get to global optimum and so on. And, this is something I do with Stephen Boyd, again, optimization expert at Stanford, because these are interesting problems also from applied math perspective.
Next question is, how would you compare recent advances in photonic optimization to recent advances in machine learning? For instance, there has been several papers that can use machine learning to predict unit cell structures.
Yes, so it's an excellent question. Machine learning certainly is just a type of optimization. We did look into it. The problem with a lot of structures that we're designing is that the parameter space is enormous, right? So I showed it at the example of a simple band, right? But even if you're designing something that is 3 by 3 microns in size in 3 dimensions, that's larger than the typical unit cell of a metasurface that people are designing. So number of parameters is so large that in order to use machine learning to optimize it, you have to train your neural network with such a large set that it is not really more efficient than doing traditional classical optimization. So while machine learning is very useful and works great for designing unit cells or smaller, maybe 1 or 2 dimensional problems. If you're interested in designing something in a full parameter space in 3 dimensions, it is not working more efficiently. For us, traditional optimization works better. But having that said, I mean, I showed that we did do some work in collaboration with Google on using machine learning to speed up traditional optimization. So I think where the strength is in this case, if you're doing very large 3-dimensional devices, is you can combine gradient descent, which is kind of traditional optimization technique, with machine learning in order to speed up optimization. In particular, we have shown that you can train your neural network as you're doing optimization to find the right basis for solving the problem. And that means that as you're, because you have seen, you know, these perturbations that you do in each step are not so large, right? You do a little bit of perturbation, so your field in the next step of optimization is very similar to your field in the previous step, which means that you can train your neural network to speed up solving electromagnetics of the problem as you're doing optimization. And for the problems where we apply this, we could speed it up by a factor of 10. And I think that's the main direction where machine learning for very large 3-dimensional structures will play a role.
Thank you. And then next question from Orad Reshif. Please tell us more about your approach to simulate the entire metasurface at once.
We're hoping to write the paper soon. I can actually just show this slide because I kind of went through this very quickly right now, and I'm happy to share the paper with you because we already have some preliminary optimization results. But the key is electromagnetic solver. Optimization is exactly the same as the optimization that we do for everything else. So it's just some adjoint optimization, gradient descent. I mean, there are a lot of different algorithms. So the electromagnetic solver that we use here is transition matrix method solver. Which means that your simulation, your meta surface can be viewed as multiple scattering from different meta atoms. So you have to describe using these transition matrices scattering from individual atoms. I mean, you know, you can pick the right basis for your atoms, and in meta surfaces, you generally know how your atoms will look like. You know, there are like some cylinders or spheres or whatever you are using. You can position them randomly, and you can also incorporate interactions between atoms into your transition matrices. And you are using these matrices to really solve the scattering from the whole ensemble. So that's what we used here, and you can see relative to simulation. So simulation size is basically the size of the meta surface. We did run this on just a simple desktop. It's much more efficient than finite difference time domain. So like finite difference time domain for 20 micron simulation size goes to something like 5 hours per simulation. We can do that in minutes, right? And I mean, of course, it still increases as you increase the size, and we're improving this and distributing to multiple GPUs. This is before distribution, but it does work much better. And we're right now running some optimizations there. So I hope to be, you know, hopefully in the next month or so, we should be able to have a paper ready.
Okay. We can wait to read it.
Yeah.
Then next question from Caterina Tabaglione. Thanks for the nice presentation and cool work about the inverse design, very inspiring. What you showed so far is all passive. How about reconfigurable PIC? Do you think it is something that can be realized with your approach?
Yeah, and actually we did design kind of reconfigurable or active devices already with this. Of course, optimization itself is passive, but you can actually do the optimization for multiple states of your device at the same time. For example, we have designed switching devices that you know would at particular refractive index route the signal to one port, and then at the different refractive index after free carrier rejection or nonlinearity, they route the signal to the other port. Your pattern, physical pattern of the device is not changing. It's only refractive index that is changing. So as you're running the optimization, you simultaneously search for the pattern that for 2 different refractive indices would perform this function, right? So that's possible right now. We do that already, right? Of course, it's two coupled optimizations that proceed at the same time. But that's no different than any multimode optimization that we normally do. I mean, whether you're doing it for two different refractive indices or two different wavelengths, you know, from mathematical perspective and complexity of optimization is not really different. Of course, there is a possibility to optimize directly nonlinear equations and include that into your the problem that you are solving. That's interesting scientifically. I'm not really sure that it brings you advantage from the optimization perspective and the amount of time that you need, because at least for all the problems that we're working on, we can always decouple the problem to multiple steady states that you can couple during the optimization and then proceed. So we didn't find the pressing need to run nonlinear optimization right away. For nonlinear optics as well, yeah.
Thank you. And then a question from Josh Baxter. He's asking basically if these techniques can also be applied in the case of dispersive materials such as silver and gold.
Yes, I mean, right now, my group's work is of course focused on the electric structures. I mean, you can add some conductivity in the problem and work with metals as well. The problem with metals is the problem that people face when they're actually running electromagnetic simulations, which is coming from the fact that the penetration depth is very small. So you need very fine discretization in order to capture the full behavior of the material. And that means that your electromagnetic simulations are, again, larger than the electric simulations that normally we do. I mean, your pixels kind of have to be much larger inside of your metallic material. Some people have done actually optimizations on the metallic structures. And early on, we also published some papers on optimization of the metallic structures using exactly the same algorithms, just by describing metals at a particular frequency with a certain conductivity, you know, real and imaginary part of the electric constant. I think it works. We haven't really spent much time on that, but I think it could be actually done. You may run into computational bottleneck again because of the fine discretization inside of the metal.
Okay, great. The next question comes from YouTube. Before performing the gradient optimization for the wavelength splitter, for example, do you use any initial guess based on some theoretical insight?
Yeah, in the past, it would just be a random guess. Then, you know, we started noticing from the optimizations that depending on how you initialize, if you initialize with something that has more of the high index material, your final structure, or it has average refractive index that is closer, for example, to silicon, your final structure will have more silicon than air. If you start with something that's closer to air, then your final structure will have kind of like more islands of silicon and more air. You know, it's interestingly, there are so many solutions in these problems that you end up somewhere in parameter space close to, well, not too far from your initial condition, right? So we did study this, and in this paper that I published here, that I mentioned here in Applied Physics Reviews, we did show for some problems like this wavelength splitter, we analyzed the full parameter space and we found the clusters of solutions, and we could get to different solutions based on how we initialized the problem. Of course, that was for that specific problem, but you know, we learned that in general, kind of refractive index value matters. And what we're trying to do now, because of course initialization is very important, you know, if you initialize it in a wrong way, then you have to travel more to get to an optimum. We're trying to learn more about how to initialize in a better way so that we speed it up. You know, you can do that for, we've done a lot of work on mode converters, wavelength splitters, so we can initialize them better. But if you're designing something completely new, you know, then you may not really know exactly what would be the good guess for initialization, but you can learn along the way. And we're trying to kind of formulate it mathematically right now with collaborators to kind of figure out more systematically what would be a better initialization.
Yeah, that's exciting too. And then another question from Mario Crane from YouTube. You write non-intuitive but automated design. Are the solutions in all cases black boxes, or have you been able to understand some new ideas from the computer solutions?
Not really. I mean, I think in many cases, right, we don't really try to explain why things work certain way. But if you are look at a particular solution, including these wavelength splitters, you can always explain why they work the way they work, right? You can look at the field profile along the directions of propagation or trajectory, and look at the refractive index, like overlap with the refractive index, and look at the harmonic of refractive index. It's kind of a combination of various scattering multiple reflections from these interfaces that leads to some constructive interference in a certain wavelength range, right? So that's kind of a general picture of what is going on, right? And I'm sure it is possible to explain it for every single thing that we've designed so far, why it works a certain way. We haven't really done it for everything, but we have been looking now more recently, in particular in the context of initialization that was asked in the previous question, trying to explain why it looks certain way, right? Because it is related to the electric constant profile along the direction of propagation. So if I know that I need to have a specific harmonic in that electric constant or something there, I can start from that, right? And then just use that as an initial condition and let me which would allow me to converge to the solution better.
And then the last question from Orad again. He's asking, on slide 19, you said, when we plot the different devices on top of each other, performance is the same. It makes sense that performance would be very similar for broadband devices. Yeah. Does this also hold for devices with high Q resonances? Do all of the resonances?
Yeah. So that's an excellent question and an excellent observation, right? I mean, because if you design things to be broadband, they're going to be more robust to certain errors, at least, right? For example, refractive index changes, thermal changes, right? Because at the target wavelength, you're just shifting the transmission characteristics left and right, or if your holes or pattern features are a little bit bigger or smaller, again, things are shifting left and right. Things are not degrading completely. And if you have resonant devices, things are gonna be more sensitive, right? I mean, of course, we use resonators. Andrea uses resonators for sensing molecules, right? So that's exactly why we use the resonators, because they're very sensitive to the environment. Resonators can be designed to be, to answer to your question, the important thing is that we do use often much higher Q resonators for a lot of functions that we need to use them. And the reason why we do that is because we know how to make high Q resonators. There is no really reason, even in WDM systems, to use such high Q resonators as the ones that we use. So you can actually inverse design 10-channel WDM system, for example, with few nanometer line width. That's not a high Q resonator. I mean, these are just inverse design elements. And if you just let inverse design things for you, it naturally doesn't come up with high Q resonances. It comes up with something that has like 10 nanometer bandwidth or so on for any function you like, if you don't constrain bandwidth, right? Because it's a more natural solution to the problem. But, I mean, what we do is we just take high Q resonators and just use that to filter or do modulation and so on, which is not always necessary unless you are doing some dense WDM. So then on the question of resonators, resonators are structures with very relatively simple parameter space and simple geometry. So if you go to resonator, then, I mean, you can try to optimize it. People have also tried to optimize it, but there is not really so much better that you can do than what people have done by brute force design. Because again, parameter space is small. You're working with very simple, like DBR reflector. There are not many holes in that mirror. You can shift them left and right and so on. And people have already done that, and they've already hit the material absorption limit of resonators. So we've done inverse design of resonators. I don't find that particularly exciting because people have already designed resonators that are limited by material absorption. What I find exciting is combining like inverse design with resonators to control their coupling to the environment, like what we did in non-reciprocal transmission, or to kind of design it in such a way that you have some larger, higher index region where you can put your quantum emitters, kind of incorporating constraints into the resonator design instead of just maximizing Q over V, which I think is a problem that people have already solved, right? I mean, you're already at the materials limit in terms of Q. So that's the answer to your question. You're completely right. I mean, if you go to a resonator, you will have more sensitivity to the environment, especially if you're talking about Q of 1 million. That's not surprising, but you don't really need to use that resonator for a lot of functions where that will be a problem. For example, optical interconnects, absolutely no reason to do it. We do it just because that's how we know to implement, how we were taught to implement WDM device.
Actually, there is also another part of the same question from Orad. Do all of the references also line up in the same locations without post-fab tuning?
Do they, sorry, I didn't hear the question. Can you repeat it?
Do all of the resonances also line up in the same locations without post-fabrication tuning?
In these WDM devices or in the resonant devices? It is related to this particular picture or the, okay. Yeah, this is, all of these are without any post-fabrication tuning. Yes, the bottom one is without post-fabrication tuning and the top one is without post-fabrication tuning, yeah. So it was just measured directly. They're all on the same chip, right? I mean, so they were nominally fabricated with the same parameters. But even when you do that in the fabrication process, things may go wrong, right? In the E-beam exposure and some errors in the position or so on. So these ones have no fully passive, no tuning at all.
Okay, so it was very exciting tutorial again. Amazing to hear all these research results from you. So I would like to thank both of our tutorial speakers once again, Abu Sebastian and Jelena Vuckovic. And please return for the career discussion panel, which is in less than 1 hour.